and maybe I'll be able to get to answer that question.
Mm-hmm.
If you look at the summary of the report, item number 1 says, the U.S. has lost its previous dominance in technology. So I'd like to go over a little bit about that technology, how it started out in the past in the U.S., where it is now, and where it's going. And so the key element, and then Phil showed in his talk this little knee in the curve of peak power versus time. And that was essentially created by the invention of chirp pulsed amplification technology. That technology, we have, by the way, the wimpiest laser here. Okay, forget it. Somewhere up there in that upper left corner is a short pulse generator. Now, in the old days of making high power lasers, solid state lasers in particular, that might be a nanosecond pulse generator. And you could only get a certain amount of energy out of that before the laser would destroy itself, but you could solve that problem by going to bigger and bigger aperture, either glasses or crystals, and expanding the beam. Oh, wow. Thank you. Yes, very good. You could expand the beam and get more and more energy, and that worked very well. The only thing in these power amplifiers that would take that oscillator and bring it up to energy, they need a certain amount of joules per square centimeter to extract energy. You just can't expand the beam too much, or you won't be able to extract energy. And it turns out if that pulse is nanoseconds, that works out all right. You won't damage the material. What if I now change over from a nanosecond oscillator into one that's producing 5 to 30 femtoseconds? This used to be a big deal. Now any graduate student can build an oscillator like that. What happens is if you need to put a certain joules per square centimeter and now divide that by 15 femtoseconds, the intensity gets so high that these materials, which are either glasses or crystals, are damaged irreplaceably and expensively. And that was a roadblock that prevented further scaling to shorter pulses and energy and higher peak powers. The invention by Donna Strickland and Gerard Moreau showed the idea of taking the pulse, short pulse in time, which is also spread out spectrally, if you will, its wavelength range, using a pair of gratings to stretch that pulse out in time, amplify that up. Now the pulse is stretched out to the nanosecond regime where these amplifiers are happy to work. You then get to high energies, and now you use the sort of inverse process with a pair of gratings. It's all a little done with mirrors and gratings, and to compress that pulse back down. So this pulse here is a chirp pulse because it's been chirped in time, if you will. And so if you look at any point in time, there's a different wavelength involved. But that gets reorganized back into a compressed pulse in that process. It's interesting to point out Donna Strickland later moved to Canada and became president of the OSA at one point. Gerard Moreau did a lot of very promising and good work early on in using this technique at the University of Michigan. NSF funding ran out. He went to France, and he's essentially the grandfather of the ELI beamlines and ELI other infrastructure in Europe now that was part of the reason this report took place because of the concern over that. Anyway, the point is to do this, you needed to get very large gratings if you wanted to get short pulses. So what happened is to get to the first petawatt laser, two things happened. One of them was very good development of high energy glass amplifiers for the laser fusion program. That went on, reminding you that the laser fusion program works with the nanosecond pulses. So it needs large glass amplifiers, but it gets up to the megajoule laser. But then using chirp pulse amplification and the large gratings, the Livermore crowd was able to get to pulses of 440 picoseconds. Nowadays, that's pretty long, but back then that was a deal. And 660 joules energy out. That was 1.5 petawatts. That was the first petawatt class laser, and it was a breakthrough. The developer, one of the developers leading the team, I was hoping he was going to be here today, Mike Perry. He's not. This is a nice picture because it shows Charlie Towns next to him getting to see what happened to the laser that he devised many years ago, the first petawatt system. What happened after that? Well, there were a couple of things that developed. That the glass was a good medium, but that's a pretty hefty laser at 1,500 joules. You saw those large slabs of glass. The Ti-Sapphire laser allowed operation with much shorter pulses, down in the 20, 30 femtosecond regime. It had the amplifier properties that would allow you to scale it, but be able to go, if you could go down to 20 or 30 femtoseconds, you needed much less energy to get the petawatt power out. And I should point out that you pay for energy. You don't pay for short pulses, but you do pay for energy because that's basically lots of glass or lots of crystals. The laser at Livermore produces a megajoule of energy, and it occupies several football fields and costs about $1 billion. If you can do with a lot less energy and still get a petawatt of peak power, you can still do a lot of the science. One of the other nice things is you could put together lots of different green pump lasers and combine them to scale up in energy. This is a picture of a 1 petawatt laser, probably the most high performance petawatt laser in the US at Berkeley Labs. It was made by a French company who took over making this as a business. They're now in the process of building a much larger system over in Europe that'll be 10 petawatts. And you can maybe see from this picture, all they've done is just make many more pump lasers using the same general scheme. There's another technology that is now emerging, which is OPCPA, optical chirp pulse parametric amplifier. It's still chirp pulse, but it's not really a laser amplifier, it's a nonlinear optical device. You need to drive it with another laser. You can use nanosecond pulses. You need pretty good beam quality. So far, these systems have produced about the same as Ti-Sapphire. Right now, they're not doing as good a conversion. The advantage is that you can scale them to extremely high energies. You're limited in Ti-Sapphire by the size of the crystal, and right now Ti-Sapphire holds the world's record for peak power at 5 petawatts in China. But the OPCPA technology can make use of enormous nonlinear crystals that are grown at low temperatures, can be made like growing sugar crystals essentially, and they allow scaling in particular in potential up to 100 petawatts or so. Now, the origins of technology, this gets back to the history. The US was really responsible for a lot of the solid-state lasers that are used in these petawatt systems, glass, YAG, ytterbium, and then Ti-Sapphire. The CPA technique, as I've mentioned, the Livermore development in other places at LLE in Rochester developed high-energy lamp pump glass lasers. You saw a picture earlier there. Large aperture gratings, more recently diode pump solid-state lasers. All of these technologies started in the US. Non-US, I think I can claim that the OPCPA concept came out of Lithuania and is scaled to petawatt powers in the UK and Russia. The Russians were really the first to develop large aperture nonlinear crystals needed for OPCPAs, though many groups, including Livermore, have scaled since then. And then the Chinese developed some of the nonlinear crystals that play prominently in OPCPA technology. In a sense, the Ti-Sapphire technology was to blame, if you will, if there's a blame, was for the proliferation of petawatt class lasers because they weren't grossly expensive and they didn't occupy a lot of space. So between 2003 and 2011, Japan, UK, Korea, France, China, all were building petawatt class lasers. And actually a commercial Ti-Sapphire petawatt class vendor emerged from France. You can now write a purchase order and get a petawatt laser. US Ti-Sapphire vendors have concentrated on a much bigger business of ultra-fast lasers for biological imaging and other applications. So they haven't really concentrated in this area.